Okay, we have been talking about dielectrophoresis, where we manipulate particles inside microchannels that are dielectric in nature, and we subject the particles to inhomogeneous electric field. Let us continue our discussion on magnetophoresis. Now, magnetophoresis is analogous to dielectrophoresis, but here we are talking about particles that are magnetizable. Okay. So, magnetophoresis is the manipulation of magnetizable particles in presence of inhomogeneous magnetic field. Okay. Magnetophoresis so magnetophoresis is analogous to dielectrophoresis, and here we talk about particles that are magnetizable. So, magnetophoresis means manipulation of magnetizable particles in an external inhomogeneous magnetic field, and the magnetic field is denoted by symbol H. Okay. Now, the dielectric response of most of the materials, biological materials, are very strong, okay, but the magnetic response of the biological materials are very weak. Okay. So, in order to achieve good magnetic or magnetophoresis in microchannels, what we do is we tag or label these biological particles with the magnetic particles. Okay. So, the magnetophoresis can be enhanced by tagging biological particles with magnetic particles. So, in that way we can selectively tag specific population of biological objects with certain types of magnetic particles, and we can separate them using magnetophoresis. So, in magnetophoresis, to achieve magnetophoresis, the dp force for most materials is strong, but the magnetophoretic force, or we call it MAP, magnetophoretic force, is weak. Okay. So, to achieve magnetophoresis, what you do is magnetic particles attached to sample. Okay. And so, in that way we can obtain control over part of the sample responding to MAP. Responding to magnetophoresis. So, as I said, most biological cells are non-magnetic, and so it is possible to label with magnetic microbeads. Okay. So, here we see an example. So, this is a polystyrene bead, okay, and which is not magnetic, and here this bead is made magnetic by having this polystyrene bead is made magnetic by having these super paramagnetic nanoparticles inside. Okay. The super paramagnetic means these these particles will go back to their non-magnetic nature when the magnetic field is taken out, that is called super paramagnetic. Okay. So, by super paramagnetic we mean that the average magnetic moment returns to 0 when external magnetic field is removed. Okay. So, when we take out, when we have a external magnetic field present, these nanoparticles will behave as if they are magnetic, and when we take out the magnetic field they will become non-magnetic. Okay. So, that is called super paramagnetic nanoparticles. So, they are present inside this polystyrene bead. So, the bead acts as a magnetic particle. Okay. On the bead we have a coating of antibodies, okay, and in a sample we may have various different types of antigens, and only the matching target antigen will bind to these antibodies. Okay. So, these are the antibodies coated onto this bead, magnetic bead, and only the matching target antigen will be bound to these antibodies, and there will be several non-matching antigens that will be also present, that may also be present in the sample, which will not bind to the antibodies. So, this is one approach how we can extract different molecules from the sample using the magnetophoresis method. Okay. So, it is possible to do magnetophoresis in microfluidic channels, where we can have these paramagnetic microbeads adhering to the wall because of an external magnet, and once these magnetic microbeads with antibodies coated are immobilized onto the wall, we can flow the sample, and the target antigen can be bound specifically to that antibody which is attached to the magnetic bead. So, this is one such case shown here. What you see here, this is a microchannel. Okay. So, this is the width of the microchannel, and we have these magnets present. These three black rectangles that we see is their magnets, and we flow these magnetic bead attached to antibody. Okay. What we see here is this is the magnetic bead attached to the antibody, which is specific to a particular antigen through the microchannel, and when you do so, what we see here, because of the influence of the external magnet here, these beads get attached to the magnet. Okay. So, they get attached to the channel wall here, as you see here. Okay. So, these beads are attached to the channel wall. Okay. What we do next is as you see here, we infuse the sample that is having different types of antigens. Okay. And when we do that, the target antigen which is specific to the antibody binds. Okay. So, this is the target antigen, okay, and these target antigens bind to the antibodies, okay, whereas the other antigens, okay, this and this, they are not target antigens. So, they just flow out along the channel. Okay. So, what we end up getting is a these magnetic bead attached to the antibodies are these antigens come and bind to the specific antibodies. Okay. Now, once we do that, next what we do is anything that is not bound is removed. Okay. So, we have only magnetic bead with antibody and attached to the target antigen, and then we may be interested in these antigen antibodies to do further biology. So, to do that we can take off the magnetic field. So, here the magnet is removed, and when you do that and we subject this bead antigen to a flow, these antigens and the antibodies can be collected. Okay, because there is no magnetic field here, we have taken off the magnetic field, these antibodies, antigens and the magnetic bead can be released and they can be collected. Okay. So, this is an example of the applications of magnetophoresis, what we can use to capture antigens and how to release them to collect to process further biology. Okay. So, with that let us look at the basics of magnetostatics. By magnetostatics we mean that the current that we are dealing with is not changing with time. So, it is invariant with time. So, under that assumption we look at the magnetostatic limit of the Maxwell's equation. Okay. So, let us look at magnetostatics. Okay. So, we basically look at the magnetostatic part of the Maxwell's equation. Okay. And here we assume that the stationary current density and any time derivative are neglected. Okay. So, under that assumption we can write the Maxwell's equation for magnetostatic in this way. So, we will have two important equation. The first one is the divergence of magnetic induction is 0, okay, where B is magnetic induction. Okay. And the second equation will be del cross B will be mu 0, which is the magnetic permeability of vacuum, okay, mu 0 into total G total current density, which will be equal to mu 0 external current density plus mu 0 the current density bound to the magnetic field. Okay. So, we have these two equations, and here we have B is the magnetic induction we already defined here, and mu 0 is the magnetic permeability of vacuum is equal to 4 pi into 10 to the power minus 7 Henry per m meter. So, this is magnetic permeability of vacuum mu 0. J total is the total current density and J external is the external current density. For example, running in a conductor, okay, and the J magnetic is the current density bound to external, bound to the magnetic field, bound to the magnetic material, and this is equivalent to the polarization charge that we talked in DEP. Okay. So, this is equivalent to the polarization charge density in DEP, polarization charge density in dielectrophoresis. Okay. Now, if we do an analogy to the dipole moment, so we do an analogy to dipole moment. So, the electrical dipole moment is charge into the separation distance between the two opposite charges. So, we can write the electrical dipole moment P as Q into D. Similarly, we can define something called magnetic dipole moment. Okay. So, similar to the electrical dipole moment P equal to Q into D, we can write something called magnetic dipole moment M for a circulating magnetization current I mag and the enclosing area A and with direction normal N. So, we can write this expression as M equal to I mag into A. So, this is along N. Okay. Similarly, we have a term polarization in electric field, we can write a term magnetization. Okay. So, magnetization is equivalent to polarization in dielectrophoresis. Okay. So, we can write magnetization M as limit the volume omega star tending to 0 1 over volume omega star integration over omega star dr into m r0 plus r. Okay. So, this is the expression for the magnetization, and r0 is the location of the magnetic dipole. Okay. So, the location of the magnetic dipole, okay, and r is at any point. Okay. So, with that we can relate magnetization to the magnetic current density. So, the magnetization M is related to the magnetization current density. You can write J mag is equal to del cross M. Okay. So, this is analogous to, we have electrical charge density, the polarization charge density is equal to minus del cross P. Okay. So, this is polarization. Okay. So, equivalent to this, in magnetophoresis we have the current, magnetic current density as del cross the magnetization. Okay. Now, we have the displacement, electrical displacement equal to epsilon 0 into E plus the polarization. Okay. This is in the electrostatic. In magnetostatic we have the magnetic field can be written as, so H is the magnetic field, is 1 over mu 0 into B minus M. So, H is the magnetic field, B is the magnetic induction, and M is the magnetization. So, now if we take divergence of the above, if you take divergence of the magnetic field, and we take divergence of H, and we use that the divergence of the magnetic induction is 0, we can find that del dot H is equal to minus del dot M. So, the divergence of the magnetic field is negative divergence of M. This is very easy to show here, because this term divergence of the magnetic induction will be 0. So, the divergence of the magnetic field will be negative divergence of the magnetization, right. Now, if you use the magnetic current density, which is del cross M, and you also use the magnetic field as 1 over mu 0 B, which is magnetic induction minus magnetization, and if you substitute that in the equation, del cross B equal to mu 0 J external plus mu 0 J magnetic. Okay. So, use these two conditions in this equation, you can show that del cross H is equal to J external. Okay. So, what do we see here? So, we have these two equations, we can say that the conclusion is that the source of magnetic field is the special variation of the magnetization and the magnetic current density. Okay. So, if we compare these two, we can say that the source of the magnetic field H is or the specially varying magnetization, okay, which is shown in equation 1. Okay. This is the specially varying magnetization, and also we have the external current density, as you see here in this equation. Okay. Now, with that we can define a term called magnetic susceptibility. Magnetic susceptibility, and this can be defined as the change in the magnetization over the change in the magnetic field at constant volume and temperature. Okay. So, for isotropic material and with hysteresis free, have no hysteresis, then the magnetization and the magnetic field M and H are parallel. Okay. So, in that case the susceptibility is a scalar. Okay. Right. Now, if we do an analogy with the electrical displacement as epsilon into electric field, we can write, okay, so we can write magnetization as susceptibility into the magnetic field. Okay. And we can also write that B, the magnetic induction, is mu 0 into H plus M, magnetic field plus magnetization, which is mu 0 into 1 plus susceptibility into the magnetic field, which will be equal to mu 0 mu r into magnetic field, which is mu into H. Okay. So, you have these two important equations, and here mu is the permeability and mu r is the relative permeability. Okay. Okay. So, with that, let us move on and try to derive an expression for the magnetic force that is acting on a magnetizable particle in a inhomogeneous magnetic field. Okay. So, let us look at the basic equation for magnetophoresis, and here we say that the external magnetic field which is unperturbed before we have the polarizable, the magnetizable object in the magnetic field is H external. Okay. So, we have a magnetic field which is X external, and this is the unperturbed magnetic field before any magnetizable object enters the magnetic field. Now, when the object enters the magnetic field, as the magnetizable object enters the magnetic field, the external magnetic field changes to some H. Okay. Now, we are trying to derive the magnetic force. Now, to derive expression for magnetic force, okay, F magnetophoresis, we need to consider the free energy of the system. Okay. So, to consider the free energy of the system, and the differential free energy, the differential of free energy of the object, the magnetizable object, is given by minus B into dH. Okay. So, that is the free energy of the system. Okay, is minus B into dH. Now, when the magnetizable object goes through some displacement in the magnetic field, we want to know what is the change in the free energy that is happening. Okay. So, the change in the free energy of object due to a spatial displacement delta r. So, d, the change in the free energy is going to be minus F into delta r. Okay. And if you analyze this equation, okay, if you analyze this equation, we get an expression for the magnetophoretic force. Okay. So, F is given by mu 0 into integration over the volume dr into m dot gradient of the external magnetic field. So, this is the expression for the force provided del cross external is 0. So, the external electric field is rotational, we are talking about a static field. Okay. Now, this is similar to what we have seen in the electric field. So, for the electric field we have seen del cross E is 0, and from that we can derive that electric field is minus del phi. Okay. So, similar to in electric field we have defined electric field is negative of gradient of the potential, here we can define something called magnetic potential. Okay. So, we define something called the magnetic potential. So, we can say H external is negative of gradient of del phi m. Okay. And for a magnetizable sphere, we have a magnetizable sphere, the expression for magnetization M. So, the expression for the magnetization would look similar to the polarization in case of the electrostatic. Okay. So, we can show that the expression for the magnetization M is 3 into mu minus mu 0 divided by mu plus 2 mu 0 into H external. Okay. And this is similar to the polarization P, which we saw 4 pi epsilon 1 into epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 into AQ E0. Okay. So, this is what we saw in electrostatic. Here in magnetostatic, this is the expression for the magnetization. So, we can write down the expression for the magnetic force. F map will be 2 pi mu 0. This is equivalent to the Clausius-Moussetti factor mu 0 mu A cube gradient of the square of the external magnetic field. Okay. So, this is at R0. So, here we see that the expression for the magnetophoretic force is very similar to the expression for the dielectric-phoretic force. In case of dielectric-phoretic force, we had the dielectric-phoretic force was varying as the square of the gradient of the electric field. Here the magnetophoretic force is square of the gradient of the magnetic field, and similar to the dielectrophoretic force, the magnetophoretic force varies as the cube of the size of the object. Okay. So, that is what we observe here. Okay. So, what we see is F map varies as the gradient of the square of the external magnetic field, and the magnetophoretic force varies as AQ, and is also dependent on something similar to the Clausius-Moussetti factor. Okay, but it is in terms of the magnetic permeabilities. Okay. So, with that let us move on and talk about the electrocapillary effect. Okay. So, first of all, what we mean by electrocapillary effect? Electrocapillary effect is the electrostatic effect at the interface between different phases. Okay. So, we look at electrocapillary effect. Electrocapillary effect is the electrostatic effect at interfaces of different phases. Okay. So, here we will be talking about the continuous electrowetting CEOW. We will be talking about direct electrowetting, DW, and we will also talk about electrowetting on dielectric, electrowetting on dielectric. Okay. EO. Okay. right. So, first let us talk about what we mean by continuous electrowetting. Continuous electrowetting means it is the electrocapillary effect that exists at the interfaces between two different fluids or liquids, okay, electrically conductive liquids that have non-zero electrical conductivity. So, in that case we would have an electrical double layer that would exist at the interface, and so because of the charge distribution, if you apply an electric field, one of the phase would start to move relative to the other, okay. So, this is what we will be seeing here. So, by continuous electrowetting we mean that it is the electrocapillary effect at interface between two electrically conducting liquid okay. So, you can see this here, we are talking about the interface between two electrical conductive liquid. So, we have one liquid here which is in the form of droplet, and this is the other liquid that we are talking about, which is the continuous phase. And because of non-zero conductivity at the interface, we would have an electrical double layer that would exist, and if we apply an electric field, okay, so this droplet here would act as a charged particle, okay, and we apply an electric field, this droplet would tend to move relative to the liquid which is 2, phase 2. So, phase 1 would tend to move relative to phase 2, okay. Now, if you do a force balance, so the force, the electrical force would try to carry this droplet and it will be opposed by the drag force, okay. So, if you look at a force balance on this droplet we will have electrical force will be equal to the drag force. So, you can write the expression for the electrical field force is Qs is the surface charge on the droplet which is into the electric field, okay. So, that is the electrical force per unit volume, okay. So, this is the F electrical force per unit volume, and so we have to equate drag force per unit volume, and we know the expression for the drag force. So, the we can assume that is Hagen-Poiseuille model, you can say it is Hagen-Poiseuille model. So, if you do that we know that the drag force is 6 pi eta a u. So, we are talking about per unit volume. So, here if you look at the droplet, it is looking like a cylinder, let us say a is the radius of the cylinder. So, we have pi a into h, okay. So, it will be pi a into h. So, that will be 6, so it will be 6 eta u over h, okay. So, this will be 6 eta u over h, right. So, what are the terms here? Qs Qs is the surface charge of droplet, and E is the electric field, eta is the viscosity, and H is the size of the droplet, and U is the average velocity. Okay. So, from here we can predict how quickly the droplet is going to move. So, the droplet velocity U is going to be, so from this equation we can find what is the value of U. Okay. So, U is going to be Qs into H divided by 6 eta L into del phi. Okay. So, that is the expression for the droplet velocity. So, the electric field is represented by delta phi over L, okay, where L is the length scale of the droplet in this case. Okay. So, let us move on and talk about direct electrowetting. Direct electrowetting is the electrocapillary effect at the interface between a liquid phase and an solid electrode. Okay. So, direct electrowetting is the electrocapillary effect at the interface between electrically conducting liquid and solid electrode. Okay. So, as you see here, we have a solid electrode. Okay, this is the electrode, and we have an electrolyte. Okay. So, in this case we can expect direct electrowetting at the interface between the electrically conducting liquid and the solid electrode. We would have an electrical double layer that would exist, okay, because the liquid is has non-zero conductivity. So, we would have an electrical, this is the electrical double layer. Okay. So, we can write the expression for the capacitance across the electrical double layer. You can write down the capacitance across electrical double layer. So, you can write C EDL will be equal to epsilon 0 epsilon r divided by lambda d. Okay. So, what we see here is that the surface energy is going to reduce because there are some charges which are going to be stored in the form of the capacitance inside the electrical double layer. Okay. So, what would happen is the surface energy reduced by the amount stored in capacitor, and so in that case we can write the relation between surface tension and applied voltage, and this is given by the Lippmann equation. Okay. So, this is can be given by the Lippmann equation. So, the Lippmann equation can be written in this form: sigma SL is going to be sigma SL 0 minus capacitance across electrical double layer del phi square divided by 2. Okay. And here delta phi is the voltage across the interface, and sigma SL 0 is the initial surface tension at 0 voltage. At 0 voltage. Okay. Now, if we combine this Lippmann equation, okay, Lippmann equation with the Young equation that we studied in capillary flows. So, combine Lippmann equation with Young equation. So, Young equation said that cos theta is going to be sigma solid gas minus sigma solid liquid divided by sigma liquid gas. So, cos theta 0 will be equal to sigma solid gas minus sigma solid liquid at 0 voltage divided by sigma liquid gas. Okay. So, we can do some math. Cos theta minus cos theta 0 will be equal to minus sigma SL minus sigma SL 0 divided by sigma Lg liquid gas, which is nothing but equal to, in the form of capacitance and electrical potential we can write this, which is going to be C EDL delta phi square divided by 2. Okay. So, from here we can predict theta is going to be cos inverse of cos theta 0 plus C EDL del phi square divided by 2 sigma Lg. Okay. So, what do we see here? We see that a surface which is originally hydrophobic can be made hydrophilic. Okay. So, if the surface is hydrophobic initially, this will be negative, right, and you can store some energy, you can take some energy out of the surface energy and dissipate store that in the form of the capacitor charge inside the electrical double layer. Okay. If you do that, the contact angle is going to be reduced. Okay. So, cos theta is going to be positive. Okay. So, what we see here that original hydrophobic surface can be made hydrophilic. Okay. So, hydrophilic means theta 0 will be less than 90, and initially it will be theta 0 will be greater than 90, and theta, let us not call it theta 0, this is theta is less than 90. So, what will be the critical potential at which an original hydrophobic surface will become hydrophilic? So, in that case cos theta 0 plus C EDL del phi square over 2 sigma Lg will be greater than equal to 0, or if we simplify we can find out that the electrical potential will be greater than equal to minus 2 sigma Lg into cos theta 0 divided by C EDL. Okay. So, we found the expression for the minimum potential that is required to make an original hydrophobic surface to hydrophilic. Now, the problem with the direct electroweighting is that the capacitance for a given set of liquid and electrode surface is fixed. So, what we can do is we can add another insulating layer on the electrode, okay, so that the capacitance, equivalent capacitance of the electrical double layer plus an insulating layer can be controlled by changing the thickness of the insulating layer, okay, and that is known as the direct electroweighting on dielectrics. So, we talk about direct electroweighting on dielectrics. So, as you see here, instead of having the electrode layer, we add one more insulating layer here. So, we have the capacitance of this insulating layer plus the capacitance of the electrical double layer. So, the capacitance of the insulating layer which can be controlled is given by epsilon 0 epsilon r over d, okay. And so, in that case we would have sigma SL as sigma SL 0 plus minus C del phi square over 2. So, we can write theta as cos inverse cos theta 0 plus 1 over sigma Lg into C del phi square over 2, okay. So, here in addition to making the surface to make a originally hydrophobic surface hydrophilic, you would have a control, and that control can be achieved by controlling the thickness of the insulating layer, okay. So, here the capacitance can be controlled by controlling the coating thickness of the insulating layer, which could be for example Teflon, okay. So, with that let us stop here.